pleasure to welcome Paolo Secchi from the University of Brescia. He will talk about the stability of the linearized MHD-Maxwell free interface problem.
Thank you. Thank you for the introduction. Thank you again to the organizer for their invitation. So this is a second talk, again on MHD equations and free boundaries. It is a joint work with my two young collaborators, Davide Catania and Marcello Dabicco. So this is the plan of the talk. The first part is just an introduction and formulation of the problem and some comment about the possible choice of the equations considered in the vacuum part. The second, where we can use the so-called pre-Maxwell dynamics. Second part, we consider the Maxwell equations. And then the third part, something about the result that we got and some ideas of the proof. Okay. So here we have the equations for ideal compressible MHD that we saw 2 days ago. We derived the equations in that introduction, where we have the continuity equation. Rho is the density of the fluid, V the velocity. Here we have the complete form of the equation for the conservation of momentum. H is the magnetic field in the plasma of the plasma region. This is the equation for H. And here we have in this long form the equation for the conservation of energy, where E is the internal energy. Okay, so we also have the pressure here, which can be considered as a given function of the density and the entropy, if we want to consider as independent thermodynamic variables density and pressure, and entropy, and another constitutive law for the internal energy here for E. This is our system of equation written in conservation form. You see, it is a system of first-order equation. This constraint that the magnetic field has to be solenoidal can be considered just as a restriction on the initial data. So if you look at the first four equations are written in conservation form with evolution time. Okay, but we take another choice of the independent variables. I consider the total pressure. It is more convenient to take the total pressure Q, and in terms of Q and still of the entropy and V and H, we can write the equations in a different way as a symmetric system. This is the symmetrization that we get when we consider Q. Another choice, good choice could be to take just P, which also can give the system of equation as a symmetric hyperbolic system, but here for us it is more convenient to take Q. Okay, and when we do this symmetrization, then we can write in a very short way the system here. So it is written as a symmetric hyperbolic system because all the coefficients of the derivative are symmetric matrices, and the coefficient of the time derivative here, A0, is also positive definite, provided that we have these hyperbolicity conditions, physical conditions that the density has to be strictly positive, and the derivative of the density with respect to the pressure also has to be strictly positive. So we have one special direction, the time, because the coefficient here is strictly positive, so the system becomes hyperbolic in the time direction. Okay, as I said before, the constraint that H has to be solenoidal can be seen just as a restriction on the initial data, and we don't put it in the system. It is only condition on the initial data. Okay, so this is...
what about weak 7? If weak 7 has someone check that is also prepared in the weaker version?
Oh, this one?
Yeah, diverging H is still also.
No, but for weak solutions, it is convenient to have, for the formulation of the problem, to have the conservative form.
Yeah, no, the divergent H is equals 0. If they should be true for weak solutions.
Probably.
Yeah, that would be nice.
Probably, yes. It comes from here. What is it?
The
Here.
divergent form.
Here.
You take
From this equation. So I can
the
take also in weak
distribution
form.
sense, yeah,
Yes, it can be done. I think
Ah,
it can be done. It's not difficult. Okay. So now we have a smooth hypersurface, gamma of t, depending on time, that we give in the form of the graph of a function. And this f will be an unknown of the problem. So this hypersurface divides the whole space R3 into parts, above and below, omega plus, omega minus. And we consider the equation that I wrote before for the MHD, only in that part in the region omega plus. So this is my region for the plasma region, see. And below,
So gamma is your free boundary.
yes, it is a free interface between plasma above and below vacuum, where we have magnetic and electric field. So this could be a simple picture. Plasma above and vacuum below in omega minus. So in omega minus, what do we consider? Okay, this is the vacuum region, where we can take the so-called pre-Maxwell dynamics. This is pre-Maxwell. Here you see in red, in the Maxwell equation, we have the displacement current, this one, that often is neglected. We can neglect this term, just write 0 here. And this complete system 4 and 5 is this pre-Maxwell dynamics. Okay, but now we see that it is enough to consider the first two equations, so for H, and given H, we can compute E, the electric field from 5. So the electric field here appears as a secondary variable that can be computed after, when you have computed H. So actually, in vacuum, only H, I forgot to say, this calligraphic H will denote the magnetic field in the vacuum region, to distinguish from the other H in the plasma part. Okay, so here we can take only, look for H, this H here, and to recover the electric field after a posteriori. Okay, we can do that. So if we consider only 4 for the vacuum magnetic field, we have our system of equations. On the interface, the moving interface between the two regions, we have to impose the Rankine-Hugoniot condition for the system, which take this form. The first equation says that the velocity of the front, F, is the normal velocity of the fluid, which means that the interface moves with the plasma. The second one is the continuity of the total pressure on one side and the other side, plus two conditions that say that the two magnetic fields on the two sides are tangent to the boundary. And this n is a normal vector. Okay, these are the boundary conditions that we impose. Possible motivation for this problem come from astrophysics or from magnetic confinement for nuclear fusion, where we have typically a toroidal configuration with many possibilities. This one, where the plasma touches the wall, but this is different from our case. This second possibility, where we have, okay, the plasma is isolated from the wall by a vacuum region here in between. This one could be the case for us. But there is a comment to do with respect to this. If we take the system for the vacuum magnetic field H in omega minus, we are considering these two equations, curl equal to 0, divergence equal to 0. on the interface, the normal component of H is 0, and also from the continuity of the total pressure, we also have this equation here. So in case B, when the system is isolated from the wall, the plasma is isolated from the wall, and all the system is isolated from outside. So on the fixed wall that I call here gamma minus, the natural boundary condition is that, again, the normal component of H is 0. So if we look to the differential equations plus this Hn equals 0 on gamma t and the similar condition on the fixed part of the boundary, this is enough to get the solution is 0 if the region omega minus is simply connected. So H is 0 in vacuum.
In the plasma region, you mean?
In the vacuum region.
In the vacuum.
In the vacuum region, it is 0.
Sure.
So we have 0, and the problem reduced to this H is 0, which it means that we try to solve the plasma equations with the moving interface, and the total pressure is 0. Q is 0 given from this equality. But this case is interesting only for multiply connected regions, where the solution of the homogeneous system for script H is not 0. Otherwise, okay. Everything is 0. So not so interesting.
But it arises in plasma physics. In tokamak is the case of isolation.
But usually they are multiply connected.
Yes,
In fact, it is.
Sure.
Yes. But it depends on the geometry. So, and then you can find H from the geometry of that omega minus, compute from there, and after that you go to solve the plasma equations with the given Q, total pressure, on the free interface. But it is a different thing. We are trying to couple the equation together and see what happens in order to study the stability of the interface. There is a third possibility. When the system is not isolated from the outside world, here, where there can be some external excitation caused by a system of coils, usually in this way. So, and usually this case is modeled by adding some additional boundary in a neighborhood of the coils and a density current, which is given, okay, because the coils are given. Okay, this is a problem that we studied some years ago. And okay, we were able to prove the well-posedness of the complete nonlinear problem under a certain stability condition that we will see after, that the magnetic fields on the two sides are not parallel. Okay, this was already done for this system. Now another possible choice in vacuum, where we take the complete system of the Maxwell equations, so we don't neglect the displacement current. So I take the Maxwell equations. Here, this epsilon is some kind of Mach number because it is the ratio of, no, it's not Mach number because C is the speed of light. V bar is a velocity of a uniform flow in the plasma part. So if this epsilon doesn't go to 0, even if it is written epsilon. It's a small parameter, but fixed. Okay, so we can take this system of equation for the vacuum, and we do that because we want to see which is the influence of the electric field, which was neglected before in the other, for the other possibility, where we studied the problem with the pre-Maxwell. And okay, we know from a paper written by Trachini on the relativistic case that a strong electric field in vacuum can give impulseness. So we are interested to see that because we expect the same. So we want to see that if E is sufficiently small, we have some form of stability. Okay, so we write the Maxwell equations in this form again as a symmetric system. to be concise. Okay, with matrices B, we couple the two H and E, the variables in W. Now, the new boundary conditions on the moving interface are this one. So the first one is the same. The plasma moves with the velocity. The front moves with the velocity of the plasma, continuity of total pressure, the two magnetic fields and tangent. And here we have to add two more boundary conditions for the electric field. And also we modified, in terms in red, the continuity of the total pressure accordingly to the new equation. Okay, so to solve the problem, what the first thing to do is to transform the domain and to fix the domain and flatten the boundary. So we introduce a change of variables, which is an unknown of the problem, of course, and transform it to the case where we have a flat boundary, y3 equal to 0, while the tangential space variables are the same. And when y3 is 0, we get f, small f is at the front, okay? And after that, we change again the letters and we write x instead of y. As before, introduce the change of independent variables here. Then we neglect the tilde and we get the new system. New system written in short form is this one, in omega plus plasma equations, vacuum equation here in omega minus, new boundary conditions, together on gamma, the flat boundary. So this is the transformation of the plasma equations, where you see that only here in the coefficient of the normal derivative, we have the introduction of psi, which gives the diffeomorphism for the change of variables. Here we have the new equations in new form of the Maxwell equations in vacuum, and the boundary conditions. But here we have 4 boundary conditions, and okay, I want to remark that we don't have the 2 conditions on the magnetic fields, which have to be tangent to the boundary, because they are just restriction, again, on the initial data. They can compute it from the equations. So they are not added here in the system, in the formulation of the boundary conditions. So we have these 4 boundary conditions for our transform problem. Okay, but here we have some comments. In fact, we have, as I said, 4 boundary conditions. But which is the correct number of boundary conditions for the well-posedness of the problem? So it is given in this way. For the complete problem, I say plasma and vacuum together, we have to see the number of incoming characteristics in the region. So for the plasma part, the plasma is above. So we have to see the positive eigenvalues on the front, x3 equal to 0, positive eigenvalues. And there is, we have 1 negative, 1 positive, so it is only 1, always 1, always 1. Plus the number of negative eigenvalues, because for B3, which is below, so entering incoming characteristic means negative eigenvalues here, plus 1 for the determination of the front, which is an unknown. Now, we see that this boundary matrix, it is the coefficient of the normal derivative in the transformed Maxwell equations. The number of negative eigenvalues varies with the sign of the time derivative of f. More precisely, if this is negative, which means that the plasma is moving downward, so expansion of plasma in the vacuum region. In this case, the number of negative eigenvalues is 2. Okay, so 1, 2, 2, 4. The correct number to be imposed is 4. And in fact, we have 4 boundary conditions, as I said before. But in the other case, when the plasma, the vacuum is expanding, is moving upward, then the number of negative eigenvalues is 4, and so the correct number of boundary conditions is 6. But we only have 4 boundary conditions. Okay, so in the case of a positive velocity, the problem is formally undetermined because we don't have 2 of the boundary conditions needed. Okay, now another consideration. In the original variables, we expect the solutions of the Maxwell equations will satisfy the 2 constraints on the divergence. True for, if it is true at the initial time, it has to be true for all times. Okay, these 2 constraints take this form after the reduction to the fixed domain with a flat boundary, with these small Gothic letters, H and D are defined with this combination, but still with the form of divergence of something. We prove this first lemma. So if the initial data satisfy the 2 constraints at the initial time, a regular solution of the transform Maxwell equation satisfy again 15, the 2 constraints for all times, if and only if the divergence of the 2 vectors is 0 on the part of the boundary where these derivatives is strictly positive. Okay, so this gives the 2 missing boundary conditions. We want to have the constraint for all times, and this is true. Of course, we require it at the initial time, but we can get it if and only if we have 0 for that part of the boundary where the 2 boundary conditions are missing. So this is the complete form of the problem. Plasma equations here, vacuum with equations Maxwell, the 4 boundary conditions that I wrote before, and the 2 constraints on this part of the boundary only. And this is a big difficulty because now we are prescribing 4 conditions on the part of the boundary where the derivative is negative, and 6 conditions on the other part. And of course, which part it is an unknown of the problem, because we don't have F. Okay, so we have, as we saw before, we have different numbers of eigenvalues on the 2 parts, which gives a different number of boundary conditions on different parts of the boundary. Okay. So this kind of problems has a name. This is it means that the boundary is non-uniformly characteristic because the rank of the boundary matrix is changing, is variable at the boundary, and there is no theory essentially for this kind of problems, only some preliminary results that I quote here.
In the part in which the plasma is retracting, what are the 2 additional boundary conditions they come from?
There is no need.
Well, you have 6 conditions.
6 conditions on this part, and 4 only this part here, where the derivative is negative. And I need the 2 conditions only on this part in order to get the 2 divergences are 0 if they are 0 at the initial time, and I need the constraints. So I have to require this only on this part. For example, Trakinin wrote a paper, a similar paper, but in the relativistic case, and he assumed to have only expansion of the plasma in order to have only the 4 boundary conditions written here without this part.
So it's very characteristic in and out, right?
In and out, yes, and changing. So
Some have changed, yeah.
2 becomes 0 in the contact point and change the sign of the other.
Have to change the direction.
Okay, but we can do something, because if we take this strange thing, these new dependent variables defined with these combinations, okay, in these new dependent variables, H and D, still in the vacuum part, okay, the transformed Maxwell equations take this form, this simple form. The Gothic letters are the same as before. Here we have the new variables defined here, and Q is a given vector depending on the transformation, and here we have the 2 divergences. So now we have the divergences of the 2 small Gothic letters H and D are 0, which comes from the restriction on the initial data and the application of our lemma 1. Then the system reduces to this one, this simple form of the Maxwell equations. We can write with the new variables the 2 boundary conditions related to the electric field simply in this form. This is the origin of the transformation. And we get, and if we consider this problem now instead of the other one, we have a problem which is characteristic with constant multiplicity in the new variables. In fact, the coefficients are constant, so it is as a constant rank. Okay, and since this is the 2 equations are just a restriction on the initial data, so if I go back here, I just take the divergence of the 2 equations. Divergence of curl is 0. So the divergence has a time derivative, it is 0, and so it is conserved, so it is 0. If it is 0 as the initial data, it is 0 forever. And so the system of the transformed boundary conditions, or the transformed Maxwell equations, plus the 2 added boundary conditions on that part, only that part where the derivative of f is positive, plus the last 2 boundary conditions for E, are a problem equivalent to this one. This one plus 2 boundary conditions written here. And now we have the advantage that the new system is characteristic with constant multiplicity. Okay. So this is the final form of the problem with the new variables in the vacuum part. Now, we know that this problem could be ill-posed. It is enough to see what happens if H is 0, for example. We get the compressible Euler equations with vacuum and this could be violently unstable because of Rayleigh-Taylor instability. So we want to see if there is a stabilizing effect of the magnetic field in vacuum and in plasma part. So we need some suitable stability conditions. And this is our stability condition. And our final goal would be to solve the problem, the original nonlinear problem, under this stability condition. And this says that this product is a vector different from 0, which means that the two magnetic fields on the 2 sides are non-parallel on the interface. This one. This is the condition. Now we want to study the linearized equations around a given basic state. We extend time, we do a lot of things. These are the properties of the basic state, some part of the equation that should be solved. Here are, after some calculations, the linearized equations. Linearized form of the plasma equations, linearized form which is the same of the Maxwell equations, linearized boundary conditions. Okay, with the definition of all the quantities, plus restrictions. Let me skip this part. So this is the result that we get. So there is a special quantity this one, depending on the basic state, mu hat, it is defined in this way. Okay, so we assume that the basic state satisfies some conditions. The last one is in a uniform way the condition that the magnetic fields on the two sides of the interface are not parallel. And here we have some smallness assumptions on V needed for the transformation that we are using. Okay, so we see that if this mu hat is sufficiently small in this sense, then all solutions will satisfy this a priori estimate, where you can see there is no loss of derivatives in u from the external source f. We get an a priori estimate which gives only tangential regularity. In the vacuum part, we have the full regularity standard Sobolev space of H and D, some regularity for these traces, and the regularity of the front is this one, H1. So we can prove this stability. We call it stability. It is an a priori estimate for the solution. If you want, it is a stability for the zero solution for the linearized equations.
So when the plasma enters the vacuum, do you have any higher regularity result for the free boundary? Or
When enters the vacuum, no, more regularity, no. It is the same, precisely the same regularity.
So
Okay.
the
I go back.
dependence with respect to delta in the constant 34.
Because we wanted to have,
You know how we go? Go to zero or go to plus infinity?
no, it is
when
fixed.
delta-
Here it in the linearized equation is it fixed. The
Yeah,
small
but I mean-
parameter doesn't,
If in 33 you take delta going to zero, then what happened with the constant in 34?
Let me see how to compare that.
everything blows up. No, I mean, no.
So
To be, this is the answer to your question, formulated in this way, because the constant depends on delta. Okay. The other problem is the physical problem. What happens when the two are not parallel? And we are studying it. We expect to find some states for the linearized equation where the problem is violently unstable, so ill-posed, and other states where it is weakly well-posed, weakly. Weakly means that maybe we will be able to show an a priori estimate with the loss of derivatives, loss of regularity, some transition to instability in some sense.
So, Paolo, I don't know anything about these things, but so does it make sense to understand the regularity of the separating region?
Yes, of course, it is crucial.
So in these
Because
theorems,
F gives the regularity of the diffeomorphism. And the diffeomorphism combined in some way enters in the matrices. It is crucial.
So, but there are no results available on this in this direction.
This one, no, and other similar results. So it is crucial to have and it seems that this is compared to the regularity of U, the lowest regularity that that one can exploit in order to close the a priori estimate. If you have less, it is.
You don't get Lipschitz.
You are not able to solve to estimate U, the solution. You need some regularity of the front. But in order to estimate the front, you need some regularity of the other. Everything is coupled. A nonlinear problem. Everything goes together. So here I have this smallness assumption for this quantity, as I said. Okay, as in the relativistic case. Possible interpretation. This parameter epsilon is very, very small. So think to give V and H, epsilon is small, so this part is okay, is small. And we give the interpretation that the electric field has to be small in order to have this kind of stability. While if the electric field is large, from Trakeening result, we expect the instability of the program. And in the other result with Trakeening, where we used pre-Maxwell in vacuum, we could choose the electric field in such a way that it was 0. And so it was more stable from this point of view. Okay, now I show you where the condition on the fact that magnetic fields are non-parallel enters, where we use it. It is very simple, because this is the linearization of the first equation for F, and given V, we can think it as a linear transport equation for F, derivative here, here, and here. Huh? You see? So we can solve it. It is simple, and F has the regularity of the source Vn. On the other hand, the other constraints on the magnetic fields that have to be tangent at the boundary can be written when we linearize the equation in this form here as a linear system of two equations for the two derivatives in space of F with some coefficients here, and the stability conditions is precisely this one, that this quantity, the determinant of the system, is strictly different from 0. We can solve the system here, find the space derivative, substitute, find the time derivative of F, and we see that the derivatives, the complete gradient of F, has the regularity of the sources here, Vn, Hn, and the other Hn, so we gain one derivative, and this is crucial. Otherwise, if we don't have this fact here, we don't have this irregularity, we only have the regularity of Vn obtained from the equation, and this is not enough. So it is more unstable. Second idea for the proof is the use of a secondary symmetrization. Here there is, given the transformation of the diffeomorphism, change of variables, we define this eta bar, this eta hat, this matrix, and we see that for every choice of a vector nu, different from 0, okay, we can take these combinations of the equations with different colors of the Maxwell equations plus the constraints, and this particular combination is a symmetric hyperbolic system. Again, this system is symmetric hyperbolic if we have this restriction on Ni. It can be also non-characteristic, depending on the choice of Ni, while the original system is characteristic, but we have the constraints. And moreover, it is equivalent. So that strange combination of equations is equivalent to the Maxwell equations. So it provided the initial data satisfy the two constraints. So for solutions satisfying the two constraints, they are equivalent. And we can take the second formulation instead of the first one. And this is more convenient, as we can see when we go to analyze the boundary terms, because if we write the new system, the secondary symmetrization just written in this form here, where we make this choice of the vector nu would have to be less than 1 in modulus, and this is one condition that I show in the theorem. Well, when we want to find a priori estimate using the energy method, multiply the solution, the equation by the solution, integration by parts, and so on, we get boundary integrals. So here in black we have the boundary terms coming from the original form of the equations, and in blue, the new terms coming from the secondary symmetrization. So new terms added that allow to play better with all the quantities. In particular, we get expanding and substituting the boundary conditions. We get all these terms here, where the coefficient of the first term written here is the mu hat. Now, this neglecting for a while the first term, I only considered all the others. This one here, and we give this interpretation. Here we have f, the front, multiplying Vn or Q or components of the vector solution. So if we say that the components have an order 0, say, and f and the gradient of f has the same order of regularity. So f has an order, roughly speaking, -1. I have products of terms of order -1 multiplied by terms of order 0. So it seems convenient, this fact, because we decrease the total order of the products. So we exploit this considering instead of L2 estimate directly an estimate in H1 time, taking tangential derivatives, substitutions, integration by parts, a lot of calculation. Okay. In the end, we can use this fact. So I go back to the first term, which is a term where we have products of components of the vectors times derivatives of f. So order 0 times order 0 in that sense. So this is more singular, more difficult. Okay, but here we use again the Maxwell equations, make a lot of calculations, write the first term, this one, as in this form, derivatives of something plus lower order terms, then make integrations. After integrations, these terms disappear. We only get the lower order terms, and in the end, we arrive at something of this form, our a priori estimate. And here you see that we need to take this number mu star, which controls mu hat, small enough in order to close the estimate. So we can, the lower order terms are estimated with terms of the same form of the terms that we would like to estimate, but they have a small coefficient in front. So.
Sorry, and the dependent with respect capital T.
Capital T the time?
Yes.
But this is, it is a linearized problem.
Yeah, but
so we
if
have
you are interested in to prove the stability to the stationary problem, then it's important to know how it depends on capital T.
I know, but after that I would like to solve the nonlinear problem to see there the dependence on capital T more. And of course I expect that everything can be done, maybe, hopefully, but only for small capital T. For large T, there is no hope.
No.
No, because the interface is going to break probably, and
No,
but also formation of shocks and.
In plasma physics, the engineer use codes for a stationary problem. Well, it depends on what condition you are putting in the vacuum, but tokamaks and accelerators,
Yes.
they used to do that.
Yeah, yes,
But
of course. Who knows? At this stage, no, this is. Thank you.
More questions or comments?
The same question, Nicola. Can you move up each is
Each?
high derivative? Yeah. I did each one, right?
Yes.
Can you move up
Yes, I think
similar way.
to yes,
Key idea here.
yes,
you might
yes, yes,
support
and
here.
think I can
You
also
take it a little bit both
find
sides and-
for every order regularity. Yes,
For
some
instance,
some time estimate. Yes, yes.
so for instance, how smooth do you think that the interface can be?
Depending on the data, the same level of regularity.
Even glitches. But your a priori estimate is only in H1.
But this one, yes,
For-
no,
for
no,
F,
but
for F,
yes,
I
but
mean.
I think that if I increase the regularity, I can,
It will win.
yes, 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 I can prove it in every HM for every M. Yes.
I would like to mention that also many people only mention the tokamak type of machine. In Spain, we have an accelerator, which is absolutely different because it doesn't have the toroidal symmetry. And in fact, to get some stability of the plasma, we have a lot of currents and coins that make the problem very interesting. It's much more complex. And I wonder if perhaps
Maybe.
this approach can be useful. It's more stable. Normally, avoid tokamak, just
Very unstable.
like a star,
Yes.
the experiments are longer than usual than in tokamaks. And when we receive in Spain some economic help from the Euratom, that was the same than the price of Figo. You know, Figo is a football player that the Real Madrid bought this player at the same time that we received the help from the Euratom, exactly the same. Euratom put the condition to build in Madrid, in Spain, a machine absolutely different with respect to any other machine in the world. And then some mathematicians were, people and myself, we were collaborating with engineers in this machine system. And we built some model for the confinement in an accelerator, stationary models.
And with the money that you received from your atom, you couldn't buy Figo?
We